We're looking at the first derivative test, and this is going to help us figure out where our function is increasing and decreasing and help us learn how to graph our functions by using calculus to help us. So recall, if our derivative was greater than 0 on some interval, we knew that our function was increasing, right? If our derivative was less than 0 on some interval, we know our function is decreasing. And so notice if we have something which is coming up and it's increasing and then turning around and then decreasing, notice this value right here. Let's maybe call it C. At x equals C, there's going to be a maximum. Point. So if we went from the opposite direction, let's say we were first looking on the left of some value and we saw that the function was decreasing. And then on the right of some value, we saw that the function was increasing. So our derivative first would have been less than 0. Increasing, our derivative is going to be greater than 0 at some value here. Let's say maybe x equals d. Then in this case, we're going to have a x equals d. There is a minimum. Point. So recall, I think this was back in 4.1 when we were looking at the extreme value theorem, finding absolute max and absolute mins. We talked about finding critical points. And so critical points, those were interior points of the domain of a function f where our derivative is going to be equal to 0, or it's where it's undefined. The derivative is undefined. And those were called our critical points of f. Okay, so we're going to use these critical points to determine where our function is increasing and where our function is decreasing, and then determining if we have some maximum value or minimum value at that point, our critical point. And so that comes to, let's actually look at a picture before I give you the first derivative test. So looking at the following picture, notice here, let's just look at all the places where our function is increasing. So where our function is going up. So notice our function is going up here from a to c sub 1. So our derivative is greater than 0. It levels out, our derivative is 0, but then it starts to increase again. So again, our derivative is greater than 0. We have again a maximum value. Or we have our derivative equal to 0. Derivative equals to 0. Derivative 0. So all the places where our slope of our function is equal to 0, that's when our derivative is 0. Or notice that peak here. This is where it's continuous, but not differentiable at that value. But that is, if we look at it, a maximum value there. And I'm just looking at all the places where it was increasing first. And those were all the values where our derivative was greater than 0. So if we plugged in any value where it was increasing into the derivative function, we would have found that that was a positive value. Our slope is positive. And then we saw that it's decreasing here at these values. And when it's decreasing, our derivative is less than 0. Oops. And so notice that it's possible to find a critical point. Those are when our derivative is equal to 0, and it's not actually a max or a min. So at that first value, C sub 1, notice that our derivative is 0, but if we looked on the left and we tested a point, we would find that it was increasing. And if we looked on the right of C sub 1 and tested a point into our derivative, we'd see that it was also increasing. So if it's increasing and then increasing again, it's not going to be a max or a min. It's where it's changing directions from increasing to decreasing or vice versa. And so in this value here, C sub 2, when we attested, if we test on the left side, we would get our positive value for our slope. On the left-hand side of C sub 2, testing a value, we get the slope was negative, and so we could see that that's a max. Decreasing to increasing, we're going to have our min at C sub 2. C sub 4, again, that's where I was saying that the derivative is undefined there because it's a sharp corner. The derivative on the left and the right of that point would give us separate values. C sub 5, notice our derivative is 0 though, but we have a function which is decreasing and then decreasing again. So that's no max or min there. Recall that if our function was continuous on a closed interval, then we could have absolute max or absolute mins on that closed interval by that extreme value theorem. And so if you look at this absolute min, this CA is our absolute min. That's the smallest Y value on the graph. The highest Y value on this graph is at C sub 4. And then we have a absolute maximum at C sub 2, an absolute minimum at C sub 3. I'm sorry, local minimum. I'm not sure if I just said the absolute. I meant local. And then local at B. Okay, so here is our first derivative test. So first derivative test, what we're going to be doing is suppose that C is a critical point of a continuous function f. So again, critical points are values which set the derivative equal to 0 or where the derivative is undefined, but our original function is defined there. And we're going to say that f is differentiable at every point in some interval containing C except possibly C itself. And then moving across this interval from left to right, we're going to look at the following. So if our derivative changes from a positive or negative to positive at C, so going from negative to positive, we're going to have a local minimum at C. And if our derivative changes from positive to negative, so we're going from positive up and then negative, we're going to have a local max at C. But it's possible, and we saw that in that picture above, that the derivative doesn't change signs at C. So it's f of prime is either positive on both sides of C or they're both negative on each side of C. And then that function f has no local extrema at that C value. Okay, so let's look at some examples. Some of these first examples were actually given what the derivative is. So we don't even have to go through that work and find the derivative. So just kind of getting used to using this first derivative test to check. And so in this example, we're looking for what are the critical points of f, on what intervals is f increasing or decreasing, and then at what points, if any, does f assume local maximum and local minimum values. So again, we got to realize that we're given the derivative function, so we don't even have to go through that work. And so we want to look at when is f prime of x equal to 0. And so looking at this, we're looking at when is x minus 1's quantity squared all times x plus 2 quantity squared equal to 0. It's already factored for us. We don't have to do that. We can set each factor equal to 0. X minus 1, I really don't need that quantity squared, equals 0, and x plus 2, I can really say that's just equal to 0. Because if I took the square root of both sides, right? square root of 0 plus or minus the square root of 0 is just 0. So adding 1 to both sides here, we get x equals 1 is a critical value. And then subtracting 2 here, we get x equals -2 is a critical value. Notice that our function, our derivative function, there's no place where this is undefined, so we're okay in that aspect. So normally once I find my critical values, I put those on the number line, and then I test values, and we're testing them back into the into the derivative function. And so smallest to largest, I have a -2 is one of my critical values, and 1 is one of my critical values. So there's 3 different intervals that we're testing. And so we're looking at for any number to the left of -2, any number, I choose to just choose them smaller, makes my math easier. If I chose x equals -3, I want to see if I plug this back into the derivative function, am I going to get a positive number or am I going to get a negative number? I actually really don't care what number I get. I just curious, is it positive or negative? And so if we think about this, plugging in -3 into this x minus 1 quantity squared, we would get -4 quantity squared. All times, well, -3 plus 2, well, that's -1 quantity squared. So notice that each place that we plug in our x, we're going to be squaring that quantity after we simplify. And so squaring that quantity, notice that we're going to get a value that's always positive. So this is greater than 0. And so since f prime of x on the left of x equals -2 is greater than 0, this tells me that my function is increasing here. And so let's now plug in some number between -2 and 1. And so if we chose, let's say x equals 0, and we go back in and plug it in wherever we see an x in our derivative function, again, we're going to get a positive number. Because we have -1 quantity squared plus 2 quantity squared, that's going to be greater than 0. So f prime of x on the right-hand side of -2, but the left-hand side of 1 is also increasing. Same reasoning as with the other instances. If I choose something bigger than 1, so x equals 2, when I plug it back into the derivative, I'm going to get back a positive number. And so it's increasing when we're greater than 1. So really what that's telling me graphically, and I don't know if I'm below or above the x-axis and I can figure that out, but basically I am increasing everywhere, but at -2 and 1, we have a horizontal slope. So we're gonna come up, we're gonna level out, and then come back up. We're gonna level out and then come back up. So we have something that's somewhere looking to that. So since it's increasing everywhere, except for those couple of spaces where it levels out and has a horizontal tangent line, this is not going to have any local maximum or local minimum points. So no local extrema. So remember, extrema was just the terminology for maximum and minimum. Okay, so let's follow, continue doing examples similar to this. And so again, we don't have to do the work of finding the derivative, it's given for us. We're given that our derivative function is the quantity x minus 2, all times the quantity x plus 4, all divided by x plus 1, that quantity, times the quantity x minus 3. We could tell that x can't be -1, right? And x can't be 3, because those are values which set our denominator equal to 0. So they actually told us two of our critical values, -1 and 3. We want to figure out where our derivative is equal to 0. And those are also critical values. So if we're looking at when is f prime of x when is f prime of x equal to 0? We're going to have 0 is equal to x minus 2, all times x plus 4. All of our denominator, really, when we're looking for our values when it's equal to 0, that denominator, it's kind of useless. Because if we multiply both sides of our equation by that denominator, it goes away. Because 0 times anything is 0. So we get that 0 is equal to our factor of x minus 2 times the factor of x plus 4. It's easy to see what values set that to 0. That's when x is 2 and when x is -4. So we actually have 4 critical values here. The places where our derivative function is undefined. So smallest to largest, we have a -4, we have a -3. Sorry, that's not a -3, that's a -1. We have a 2, this is not to scale, and we have a 3. So there's actually a lot of different intervals that we have to look at here. We have to recall, though, that it's undefined. It's a kind of open circle, and -3 and 3. So if it's, yeah, well, that's actually just our original function. I'm sorry, that's just our derivative function. We don't know about that for the original function. So let's start testing points. So let's look at the left-hand side of -4. So something smaller than -4, and we're plugging it into the derivative. Let's just think about positive and negative numbers to see if this result's going to come back positive or negative. So let's say we chose x equals -5, and we plugged in f prime of -5. Well, if we plug in -5 minus 2, I'm just going to think of this as negative or positive. That's negative. If I plug in -5 plus 4, that's also negative. All divided by, so -5 plus 4, that's a negative number. And -5 minus 3, this is negative. So I noticed that multiplying two negatives together in the numerator is positive, two negatives together in the denominator is positive, positive over positive is positive. And so this is equal to a positive number, so that's greater than 0. So that tells me that my function is increasing on the left of -4. So let's look at what's happening between -4 and -1. So again, just choose some number between -4 and -1. So how about x equals -2? If we plug this into the derivative function, we want to see our value is going to be positive or negative. I'm just trying to see, is our derivative function positive, greater than 0, less than 0 in the derivative. If we plug in -2 into the first parentheses in the numerator, -2 minus 2, so that's negative. -2, though, plus 4, that's positive. All over -2 plus 1, so that's negative. And -2 minus 3 is also negative. So negative times positive is negative, and a negative over negative times negative is positive. This is a negative number. So this is less than 0. So we know that it is decreasing. Between -4 and -1. Okay, so increasing to decreasing, that tells me that this is going to be x equals -4 is a max. Or a max occurs. We'd have to figure out what the original function is and plug it in, which you don't know, to get what that maximum value is. So now let's look at a number between -1 and 2. So how about x equals 0? If we plug this into the derivative function, we get 0 minus 2, so that's negative. 0 plus 4, that's positive. Oops, I don't need to write the 4. All over 0 plus 1, which is positive, and 0 minus 3 is negative. So a negative divided by a negative, which is equal to a positive. It's greater than 0. So now we have something which is increasing here. Our derivative in that interval was greater than 0. So x equals -1 is a min occurs as long as x equals -1 is defined for f of x. So choose something between now 2 and 3. And so how about 2.5? So plugging in 2.5 wherever we see an x in our derivative function. 2.5 minus 2 is positive. 2.5 plus 4 is positive. All over 2.5 plus 1 is positive. Excuse me. All times 2.5 minus 3 is negative. So I notice this is less than 0. So it's decreasing. So again, so increasing to decreasing, that's a max value. So a max occurs at x equals 2. And the last one, let's look at to the right of x equals 3. So let's plug it in 4. So if we plug this back into our derivative function, 4 minus 2 is positive. All times 4 plus 4 is positive. All divided by 4 plus 1 is positive. Divided times 4 minus 3, which is positive. So this is greater than 0. So I know that this is increasing on the right-hand side of 3. Okay, so when they did state this, that the derivative or f prime of x is not defined, or just as x is not defined at -1 and 3. So that meant for the original function. So really what's happening there is you have an asymptote. And so remember at vertical asymptotes, things can be changing on either side of our asymptote. But if asymptotes are where vertical asymptotes are where a function is undefined. And so you can't have a max or min where it's undefined. And so in this case, and this is why I kind of put the open circles there at first. So at x equals -1, we do not have a minimum. I'm just going to erase that piece. If it was defined there at -1, we'd have them in. And if it was defined at x equals 3 on our original function, we would also have them in. But because they're undefined at our original function, we can't say that there's a max or a min there. Okay, so one more, similar to what we were just doing, finding our critical values and then testing to see where a function is increasing, decreasing, and if we have any max or min values. So f prime of x is equal to the quantity sine x minus 1 times the quantity 2 cosine x plus 1. And we're given that x is between 0 and 2 pi and including. So again, we want to find out when our derivative is equal to 0. So we can set each factor equal to 0. So we're looking at when is sine of x minus 1 equal to 0, and when is 2 cosine of x plus 1 equal to 0. So if I add 1 to both sides, this is sine of x is equal to 1. We could take the inverse sine of both sides or think backwards. What value of x, sine of what value gives you back 1? Well, sine of pi halves is 1. So when x is pi halves. So now let's look at the other function, 2 cosine x plus 1 when that's equal to 0. So let's subtract 1 on both sides. We get 2 cosine of x equals -1. Divide by 2, we get cosine of x equals -1/2. So now we're trying to think about what values of cosine of x gives us back -1/2. Well, let's just first think about cosine of x is equal to +1/2 in the first quadrant when x is pi thirds. So cosine is negative in our second quadrant. So our reference angle is going to be pi thirds. So think to ourselves, pi minus pi thirds, or 3 pi thirds minus pi thirds. That's going to be 2 pi thirds. So when x is 2 pi thirds. It's also, cosine is also negative in the third quadrant. So our reference angle of pi thirds here, well, if we add to our pi thirds, so 3 pi thirds plus pi thirds is a 4 pi thirds. Okay, so we're starting at 0. We're going to pi halves. Again, this is not to scale. We have a 2 pi thirds and a 4 pi thirds. And we're stopping at 2 pi. So we're going to go in and we're going to test our intervals, plug it back into our derivative function to see if we're positive or negative. So I'm going to choose values. I know what my trig functions are. So if I was choosing something between 0 and pi halves, well, I know pi force, what sign of pi force is. So maybe let's choose x equals pi force first. And we want to plug this back into our derivative function. So f of pi force this is equal to sine of pi force minus 1 all times 2 cosine of pi force plus 1. Yeah, and really all we have to worry about is this positive or negative. Well, sine of pi force is √2/2. And square root of 2/2. Yeah. is 0.7. So that's less than 1. And so this is a negative number here. And this is going to be positive. So this is going to be less than 0. So this will be decreasing between 0 and pi halves. So let's look at something between pi halves and 2 pi thirds. So how about 3 pi fourths? So plugging it back into our derivative function. Again, we're only worried, is it positive or negative? Well, sine of 3 pi fourths, that is the same as sine of pi fourths, root 2 over 2 minus 1. That's a negative number. Cosine of pi fourths, that's root 2 over 2, but it's negative root 2 over 2. Our 2's will cancel. And so we have negative root 2 plus 1. Well, negative root 2 is bigger than negative 1. Well, smaller than negative 1. So that's going to be a negative number. And so we have a negative times a negative. So this is going to give us something greater than 0. So choose something between, how about 2 pi thirds and pi fourths? So pi falls there. Let's say check it, x equals pi. So if we plug it into our derivative function, sine of pi, that's 0. 0 minus 1 is negative 1, which is negative. 2 times cosine of pi, well, that's negative 1. So 2 times negative 1 is negative 2. Negative 2 plus 1 is negative. So I get this is greater than 0. And then one more, something between 4 pi thirds and 2 pi. So how about 3 pi halves? So looking at the derivative of 3 pi halves, well, sine of 3 pi halves, that's negative 1. And then negative 1 minus 1 is negative. 2 times cosine of 3 pi halves. Well, 3 pi halves of cosine, that cosine of 3 pi halves, that is 0. So we have 0 plus 1, which is positive. So this is less than 0. Oops, I forgot to do the others. This was greater than 0. So we're going up between 2 pi thirds and 4 pi thirds, but from 4 pi thirds to 2 pi, we were going down. The derivative was negative. Okay, so let's look at each critical number. So from our pi fourths, we have something that's coming, or pi halves, we have something coming down and then up. So we have a min occurs at x equals pi halves. Then we have something that is increasing to increasing. So x equals 2 pi thirds is neither a max nor a min, occurs there. And then at 4 pi thirds, we have something which is increasing and then decreasing. So increasing to decreasing, that gives us a max occurs at x equals 4 pi thirds. So looking at the following graph, you should be able to tell where it's increasing and decreasing. You should be able to identify where local and absolute extreme values occur. In this graph, we're assuming that the function is not continuing in the direction as x goes to negative infinity or positive infinity. So these are closed circles here. And so let's just look at where it is increasing. So we're increasing here from -4 to -3. Union, we're going up from the x values that we use. So -1 to +1. And we're going up from 2 to 4. So this is where we're increasing. We're decreasing where our function is going down left to right. And so we're going down starting at -2 until -1. Union 1 to 2. So x equals 3, -3. Notice that this is a maximum, but it's not the highest point there. So this is a local max occurs. And remember the maximum value or the min value, those are the y. So the at x equals -3, a local max occurs and is 1. We also have this point here at x equals 1. So again, a local max occurs at x equals 1. And the value is 1. So if I'm looking at x equals -1, that is a minimum value. And notice that's the smallest value on the graph. So x equals, at x equals -1, we have an absolute min of -1. Here at x equals 2, we have a local min of 0. Notice we also have a local min here at x equals -4. Because our n value is a solid circle. And local max and local mins, or absolute max and absolute mins, can occur at our n values. And here, notice at x equals 4, that's the highest value we're reaching. And so at x equals 4, we have a absolute max. And that's of 2. Looking at a graph, you should be able to tell where it's increasing, decreasing, where local max, local mins, and absolute max and absolute mins occur. Okay, so that was the end of that section. Let me stop the video and put a video of homework problems.